Okay, this is chapter 3, day 5. We're now going to start putting it all together. So we'll have a graphing calculator, and mine's pre-loaded, so you may have to stop the video and load it up. Let me get my face in here. So this is an old prompt. I like it. We don't really think in terms of televisions anymore, but I don't know, think in the early 2000s before all the cell phones and everything came out. There was a really cool study. It was an observational study that looked at how many people there were per television, their life expectancy. And of course, there's a relationship. It's not cause effect. It's obviously correlative because having lots of TVs just represents having lots of money. So you can see some of your favorite countries in here. So the US has 1.3 people per TV. I think that what that means is like if there's 4 people in a house, there would be 3 televisions. Is that right? Right. So in Vietnam, at the time of the study, it was a little more poor. You can read the list there. Okay. So it just represents wealth. Again, this would probably be different today, but it's an old study. I kind of liked it. And obviously, you realize that if you increase the number of TVs in a country, you're not going to increase life expectancy. We all know that. So it's a correlative study, not cause effect. All right. So the explanatory variable is X. And again, explanatory just means it's the X, and people per TV is that. And the response variable is life expectancy. So I went ahead and typed all these in my calculator. So what I'm going to do first is I'm going to go ahead and bring over the calculator here. Let's go zoom, see your stat edit. I went ahead and put in L1 and L2, all those numbers, okay? So when you graph it, you go second y equals, and you got to go to plot 1 and make sure you are on this guy that's flashing there, the little flasher, and he's that means bivariate data. You got to put in L1 for your list. How you do that is second and the 1 button. And then how you do L2, of course, is second and the L2 button. Then I always hit zoom and the number 9 because 9 means it'll fit it in there. Now that is not what's on your notes. What's on your notes is I removed Haiti. Haiti is an extremely poor country, and it's right here. It's an outlier. So with Haiti, you really have like a nonlinear function, right? Without Haiti, it actually looks fairly linear. Okay, it couldn't break through this x-axis here, which means you would live forever if you have enough televisions. So we don't have that situation. So, okay, so you could draw this real quick in the corner of your notes with Haiti. You might want to label Haiti because Haiti is clearly an outlier and is very different. What's the definition of an outlier? An outlier, once again, is when you remove it, there is a significant change in R, and this is a significant change in the slope. The definition of significant is subjective, however. Okay, but you can tell this is going to be is a powerful thing. All right, so let's go ahead and get all the particulars. So hit the stat button, hit the calc button, and go down to number 8. Number 8 is the one we use on our calculator. Number 4 is the same thing. It just has A as the slope, but I want to train you that B is the slope for us. So A plus BX. Hit enter. Some calculators you'll have to type in L1 comma L2, and the comma is above the 7 if you have an older version. On mine, you type in L1, L2, go down to here and hit enter. And there it is. What's kind of nice is you get R squared and R as well. Okay, so here is A. I could round to 70.2 if I wanted to. Here's the slope, 0.14 if I rounded. Here's R squared and R. Now, let's say R squared and R did not come up on your calculator. No problem. If it doesn't come up on your calculator, you're going to go, let's see here. We got to get to the catalog. So where is catalog? Yeah, second and the 0 button. That's where catalog is. Second 0, and you're going to go to diagnostic on. That's the D. There's a faster way to get there, but we're just cruising here. Okay, so You're going to go to diagnostic on. And your diagnostics, there's a lot of things that are turned on when you do that. Hit enter. There's a lot of things that happen, but one of them is it turns on your R&R square. Okay, fine. I hit it twice. You didn't need to. So I'm going to go stat calc 8. Got all that. There it is. So hopefully that helps. Now I'm going to lower this, and I've written all that down here. Okay, for the first one, although I don't like how I did it. I wish, usually it's written the other way with these this way, 70 point, and then put the slope second, but it's the same thing. Okay, this one with Haiti removed, that is this drawing right here. I removed Haiti, just so you know. Okay, so what I want to point out here is the R value with Haiti is in the mild range. And remember, mild is subjective, but strong is negative 0.8 to negative 1 for a negative trend, positive 0.8 to positive 1 for a positive trend. Mild is 0.6 to 0.8 or negative 0.6 to negative 0.8. And then weak is in between negative 0.6 and 0.6. That's my definition. They are all subjective. But just to help you, for a word, strong, mild, or weak, that'll help you. Okay. All right. Now, so there is the R value. We're in the mild range. Look what happens when Haiti is removed. You redo the whole thing. I did that. Take Haiti out of there and redo it. The slope jumps dramatically, and the y-intercept jumps dramatically, and R jumps from mild range to very strong negative. And you can see this is very linear without Haiti. Look at the difference between that, and let me bring up the other one. Okay, zoom 9. I mean, what a difference that 1 point makes. That's an outlier. Okay, and that influences. Remember, an outlier's removal will dramatically change R&R squared because they're non-resistant, and will also dramatically change the slope. Look at that slope. It multiplied by like 4 because of that point being removed. Okay, so let's walk through some of these questions down here. Now, you might consider writing the answer to what I say and pausing the video to the stuff we're going to do. You might want to, we're going to do this twice. So you might consider, writing the answer down. So what does R mean in context? What's his name? Okay. So if you use this one right here, R would be, there is a mild, negative, linear relationship between people per TV and life expectancy. If you use this one, it would be, there is a strong negative linear association between people per TV and life expectancy. That's a good sentence frame for it. It's very easy to remember. Okay. Remember, R is non-resistant to outliers. It'll change dramatically when you don't have it. Okay. Let's go to the next question. Again, you might consider pausing and writing that down. What does R squared mean in context, and what's its name? R squared is a percentage. So let's just use one of them. Let's just use this one and make it negative 0.7. So R squared will be, by the way, R squared is always positive. It'll be 0.49. So here's your sentence frame. And again, you might want to write that down. 49% of the variability in life expectancy is due to people per TV. That doesn't mean cause effect. That just means within the problem. 49% of the variability of life expectancy is due to people per TV. Okay, that's if you use that one. All right, so that's the second question. The third question is, what is the equation of the least squares regression line? Define all variables. This happens once in a while where they give you a kind of a printout. We'll do it later in the week, do it later in the lessons, I should say. So in this case, make sure that you would point out that y hat equals predicted life expectancy. Put the word predicted life expectancy, okay? And then X is people per television. You have to write that as well down here. Not just the equation, but what X equals and what Y hat equals. Okay, that's what they want. All right. So there's that one. Scroll down. Let's pick up the place a value in X to produce a Y. No problem. It'll be worded like this. So let's say there are 30 people per television in a country. What is the life expectancy? No problem. Okay. So what I'm going to do is I'm going to go second quit. I believe the formula is, oh, there you go. Perfect. I'm going to go point, so you're clear, negative 0.137 times 30 for the 30 people plus 70.173. Okay, it'd be 66. So that's what happens when you place a value in the word a question like that. Okay, the next one is put a value in Y and work backwards. So let's say it's something like this. They ask you the life expectancy of a country is 70, exactly 70. How many people per television? So you put 70 in for Y hat right here. I'm going to use the original one. Negative 0.137 X plus 70.173. Okay. And then you have to solve backwards for that. So in this case, I would go 70 minus 70.173, enter. And I'm going to divide that by negative 0.137. And it's about 1.26 people per television. Okay. So there is how to do that. Now that's pretty simple. That's simple algebra. Okay. So let's go down to the next question. What does the slope mean, number 6, in context of the problem? Yeah, you got to know this one. What does slope mean? Okay, again, write this down. The slope is right here. And it's a for every problem, means for every. So for every a person per television, life expectancy is expected to decrease by 0.137 years. 0.137 years is a month or something, so not very much. Okay. So, all right. So there's that. What is the formula that involves slope correlation, and standard deviation? You need to know this. It's actually on the formula sheet, but it's B equals R times S sub Y over S sub X. Just remember that, or it's in the formula sheet and look it up. It'll come up, they'll ask you what the slope is of something. How do I get that? And you realize, oh, they had given me the standard deviations of the Y's and the X's, and they'd given me R so I can put it together, okay? Number 8, resistant and non-resistant. In this case, all right, not everything we're doing is non-resistant, basically, okay? So the slope is non-resistant to outliers. R is non-resistant to outliers. R squared is non-resistant to outliers. So everything we're doing here is non-resistant. Just so you know, there really isn't anything that's resistant in this situation. Okay, is the line a good fit for the data? All right, so let's say you had, let's go back to this here. This is good. I got a really good situation here. So let's go back to the original graph. This is with Haiti, okay? And I did a stat calc 8, and I told it L1, L2. We've done that before. I'm reviewing here. And you get that. So what I want to do is I want to type this into y equals. There's a couple ways to do it. One, you could just type it in. And two, the calculator actually saves the last regression line it did. So you can go to vars, it's right up in red, and then go down to statistics, number 5. And then you go to equation, and there it is, regression equation. Okay, so it doesn't round at all. And you can just hit graph or zoom 9 or whatever will work. So is the line a good fit for the data? Remember from previous lessons, does this pass the eyeball test? The answer is clearly no. This doesn't fit it. You would say this doesn't fit the eyeball test. You got an outlier there. It looks like it'd be a curve, if anything. Okay, we can actually find a better fit for this on the playing with it on the calculator, find a better fit. I don't want to do that today to get you all confused, but it's not a good fit for the data. It's really obvious it's not. Okay, and you would say it just looks like it has a curve to it. If there was a residual plot, it would be very messed up. It would not be randomly scattered, if you remember that from previous lessons. Okay, so is the line a good fit for the data? Not with this one, but I betcha if you did let's see here, if you did this thing with a line, it would come out great. A line would really be a good fit here. It would be pretty good. Okay, and I'm assuming that if you did this one, if Haiti was removed, that thing would be like right through here. And then if you did a residual plot like we did the other day and turn it on its side, it would be fairly randomly scattered. You know what I mean? It would be pretty good. Half above, half below. So you'd say, yeah, the line's a good fit for the data because it looks linear. And if I did a residual plot, or you could show one real quick, you could draw it real quick, like we practiced the other day. You'd say, yeah, it's a good fit for the data because the residual plot does not show a pattern. Okay, it's pretty cool, huh? So what is the meaning of least squares? Okay, this is kind of nice to know. You might want to write this down. The meaning of least squares, I'm on number 10, by the way, in case you're a little lost, I'm on number 10. The meaning of least squares. The meaning of least squares is it's the line that minimizes the sum of the squared residuals. And we're going to look at that a little closer in subsequent lessons, but that's good to know. What does an outlier influence the problem? What did Haiti influence? Haiti influenced R squared, which is the same thing, I guess, and slope. Sometimes it could influence the y-intercept. It could. Okay, it could. But these are the ones it really affects. Okay. An influential point an outlier is an influential point, but an influential point is a little bit different. Let's talk about 12. Let's make up a situation where this works. All right. So let's say you had this. This is the problem with Haiti removed. Haiti removed is right here. So let's say we had this right here, right? And let's say a point came in right on the line, way out here, but it was right on the line. That would not change the slope, but it would increase R a lot and make it look more correlated than the other points may be. So let me repeat that. An influential point is usually right on the line, but very far out on the x-axis. And it keeps the slope the same, but jacks up or artificially inflates R or R squared to make it look more correlated than it may be. That's an influential point. Okay. And then lastly, what does S on the mini-tab printout? We'll see that later. We'll see that soon. We haven't seen it yet, but I'm getting you ready. Let's say there was an S number here like this. S equals, I don't know, 1.2. Okay, well, this is really easy, so write this down. Let's say S is 1.2. So put on your notes, if S is 1.2, then you would say the typical prediction for life expectancy is usually off by 1.2. Okay, so if this line is going through here and it's pretty good, notice that they're not off by much. All they do is basically average how far off the residuals are. That's really what they do. It's not quite an average as in absolute value, but the mechanics of it are pretty close to that. So what it is the typical prediction is off by 1.2 years. And the prediction is the Y value. Okay. So let's go through this situation all over again with a new set of data. Okay. And we're going to do some other stuff like switching X and Y and junk like that. It'll be fun. Okay. So what I did in my calculator is I went ahead for this lesson and I put, get rid of this. I put this in L3 and L4. Okay. This is weeks on a diet and pounds lost. Weeks on a diet. So first week on the diet, you lost 6 pounds. Third week, you lost 8 pounds. Fifth week, you have 11 pounds lost. Whatever. Okay, so that it's you got this. Okay, I'm gonna go ahead and graph this. Second Y equals. I'm gonna graph L3 and L4. Okay, so there it is. Looks pretty linear. This one's a little weird, this point down here, but it's pretty linear. Okay, not bad. I'm gonna go stat, calc, 8, and I'm doing it for L3 and L4. Remember, you may, if you have an older calculator, type in L3 comma L4. Okay. Calculate. So there we go. Okay. So there's the A, there's the B, there's R squared and R. Okay, so R is in the high mild section, 0.78. Okay, and if I were to graph it, I'm going to type it in this time. So 6.3 plus 0.55x. Okay, so 6.3 plus 0.55, and then x is right here, xt theta and n. Okay, if you can see, it's lit up in red there. I'll just put zoom 9. So there it is, pretty good. One of them hits it right on the button. So you have two positive residuals up here, 2 negative residuals down here, and one with basically a 0 residual. And if you recall, the residuals add up to 0. They add to 0, which is good. Okay, and that's why you square them. And this line minimized the sum of the residual squared. There's no other line that'll do any better. That's kind of how it's calculated. Okay, so let's go ahead and get this to the side here. Okay, there we go. I can fit it in the same screen. Awesome. All right, let's try this. So as we go through this, there is the prediction line. Okay, I rounded it. There's R squared and R. We've calculated that. Now, we're going to learn a little bit about correlation here as we do this. We're going to learn a little bit about it, okay? About R, the correlation coefficient. So here we go. Okay, I got this half and half, basically. Okay, so let's switch X and Y and recalculate everything. Let's try this. Let's switch X and Y. Okay, so on my calculator, I'm going to go, let's see here. Stat, calc, 8. I'm going to switch L4 and L3. Okay, so instead of pounds lost will suddenly be the X and weeks will be the Y. It doesn't make sense. Let's just see what happens. Okay, let's look at what happened. Look at R squared and R. Compare them. They stayed the same. So compare this right here with R squared and R. They stayed the same. Now the slope and the y-intercept changed, but R and R squared did not. Why is that? The reason that is because R is unitless. Remember that. R and R squared don't have units. There's no miles per gallon, no pounds per week. There's none of that. R and R squared measure a relationship. And the relationship is the same no matter what you say about X and Y. It doesn't make any difference. So that's an important thing to know, to review. R doesn't have any units. And if you flip X and Y, R will stay the same because it's just measuring the relationship, the strength of the relationship. Okay. Now, the next part, part B, this is pretty cool. Part B, add a consistent number, say 3 to pounds lost and recalculate it. No problem. Okay. So let's do that. Okay. So I'm going to add 3 to all these numbers right here. Okay. I'll do it in, let's see, I'll slide this over a bit. I'll do it right here. So I'm going to add 3 to all these numbers. So this will be 4. Okay. Hold on a second. Let's follow the directions exact. So I'm going to go 1 here. 3 to pounds lost. So let's do it exact. So I'm going to add 3 to this. That'll make this 9, enter, 11, enter, 14, enter, 12, enter, and 16, enter. Now I'm going to go to second quit. I'm going to go stat, calc, and I'm going to go down to number 8. Okay. And I'm going to go back to L3, comma, L4. Okay. And I'm going to hit calculate. What changed? The slope did not change. Notice that the slope didn't change. Okay. But the y-intercept changed, right? But r and r squared did not. So again, that relationship will be the same if you systematically change it by the same number. Okay. Now, let's do the diet column by 2. We're going to multiply the diet column by 2. That's this one right here. And let's see what happens. Multiply the diet column by 2. All right. So stat. I think I can do this all in one shot here. I'm going to go to L3. I'm going to go L3 times 2. See if that works. Yeah, I doubled it all. Okay, doubled it all. Now let's see what happens. Okay, second quick. Stat. Calc. 8. L3, L4. Again, look what happened. The slope did change. Okay, the slope did change. The y-intercept changed, but r and r squared did not. That's really important to know. Again, r and r squared measure relationship. And if you consistently change the relationship by the same factor, it'll never change, even if you flip it backwards. So that's something to know. Does that come up a lot? No, it doesn't, but it does come up periodically. Okay, so that is A, B, and C on that. Okay, so what I want to do right now is I want to go through the verbiage again. Let me go back to the original data on this real quick. I might need this. Let's see here. 1, enter, 3, enter, 5, enter, 9, enter, 10, enter. Okay. Whoops. And then 6, enter, 8, enter, 11, enter, 9, enter, 13, enter. Okay. So let's graph this. Let's go stat, calc, 8, L3, L4. Let's correct this again. I'm gonna get this in here. All right, fine. That's the original. Let's go zoom 9. Okay, so that's the original. There we go. We got it back. All right. So I'm going to slide down here and let's work on this. Okay. What does R mean in context of the problem? What's its name? Maybe you write this down this time. Maybe you choose not to. I'm not sure. What does R mean? So R originally was 0.789. That's really close to strong. So I'm going to use a qualifier like very. You ready? So remember, strong, 0.8 to 1, mild, 0.6 to 0.8, or moderate, either way. So I'm going to say there is a moderately strong, maybe I'll say that, moderately strong or moderate, there's a moderate positive linear correlation between weeks on a diet and pounds lost. Okay. So it's 3 words you need: strong, mild, weak, positive or negative, and you always have the word linear. So again, there is a mild or moderate, strong, moderate, positive linear correlation between weeks on a diet and pounds lost. Okay, what does R squared mean? Oh, by the way, the name of R is correlation coefficient. What does R squared mean? What does R squared mean? It's a percent. You ready? It's a percentage, and it's right here. 62% of the variability in pounds lost is due to weeks on a diet. Variability in Y due to X. I'll say it again. 62% of the variability in pounds lost is due to how long you're on the diet, which makes sense. A lot of the reason you lose weight is how long you're on it. Makes sense. That accounts for over half. Okay. Next one. What is the equation? Define all variables. Number 3, no problem. So when you do that, it's right here. You just have to make sure you define Y hat. Y hat is predicted pounds lost. X is weeks on a diet. Okay. Place the value in X to produce a Y. Let's do that. So let's look at the equation here. Let's say you got, let me go second quit here. Let's say you're going to be on the diet, I don't know, 7 weeks on the diet. Okay. And again, the prediction model is supposed to work between 1 and 10 weeks. If you go outside of that, it's probably going to be iffy if it works. That's extrapolation. It's supposed to work between 1 and 10. So let's just say 7. So if I do 7 weeks there, what I'm going to do is I'm going to do 0.554 times 7 plus 6.297. And you are predicted to lose about 10.2 pounds. Okay. So that's placing a value in Y to get X. So let's say somebody says, I would like to lose a quick 10 pounds. How many weeks do I need to be in the diet? In that case, you're going to draw out 10 equals 0.554 X plus 6.297. Sorry about my writing. 6.297. Okay. So what I'll do then to use my algebra, I'm going to go 10 minus 6.297, enter, and then divide that by 0.554. It's about 6.7 weeks, something like that. Okay, so that's that one. All right, which is pretty cool. So slide down here. I've done. What does a slope mean in the problem? What's its value? I'm going to add one in there too. So what does slope mean? Again, here's the slope right here. It's a for every. This is a good one. For every week you're on a diet, you are predicted to lose about a half a pound. Okay, because 0.554 is about half. So every week you're in the diet, you're predicted to lose about a half a pound. You want that sentence to make sense as much as you can in context of the problem. Okay. What I didn't have on there is what's the meaning of the y-intercept? This is a great example. We've talked about it in other videos of being an unrealistic number. This prompt is between 1 and 10 weeks. It doesn't really, it's not meant to include 11 through 20 or 0, right? You can't have negative weeks. What this means is if you're on the diet 0 weeks, you are predicted to lose 6.297 pounds. That is not realistic. Sometimes the y-intercept is not realistic, and this is one of those problems. So that would be a good one to remember. Okay, I added that one. That's not in that list. Okay. The formula that involves slope, correlation, standard deviation, I've done that before, but I'll write it out again. You want to remember that B equals R times S sub Y over S sub X. It does pop up in multiple choice. They'll give you 3 of the 4 numbers, and you got to solve for the 4th. Okay. Resistant and non-resistant mean, what they mean is outliers or influential points will not affect things that are resistant. Medians are resistant, but anything to do with a mean or an average is non-resistant. Everything in chapter 3 is non-resistant. Right? I guess you should probably already know that, but things that are non-resistant, once again, R squared and R, non-resistance. Slope, non-resistant. That's the main things. Is a line good fit for the data? You be the judge. All right, let's go back to the graph. Let's check this out. Does it pass the eyeball test? Sure. Could we make a little residual plot? We could. This point's down here. This point's on the line. This point's up here. This point's up here. This one's down here. Does it look randomly scattered? There's so few points, it's kind of hard to tell. But yeah, there's no pattern to that. It looks randomly scattered. Yeah, it looks randomly scattered because the line looks like it's a good fit for the data. The residual plot that I drew is randomly scattered, and R and R squared are relatively high. That'd be a terrific answer to mention 3 things. The eyeball test, you could mention the residual plot, and you could mention R and R squared. That's a great answer. All right, what is the meaning of least squares? I'm down to number 10. Least squares means this is the line that minimizes the sum of the squared residuals. These are residuals, these vertical lines that I'm drawing, okay? If you add them up, they make 0. But if you square them, you get a value. And this line minimizes that squared value. I hope that helps. Okay. What does an outlier influence in the problem? An outlier will influence, of course, R and R squared and the slope. What does an influential point do in the problem? An influential point does not affect slope. It does not, because it's right on the line, but way out there. But it does artificially inflate R and R squared. Okay. And then the S on the mini-tab printout, which we're going to see soon, I promise, we're going to see that soon. Okay. If there's the value of let's say S equals 1.3 in this case. If there was that number, it would be the typical prediction for this problem is off by 1.3 pounds, which is good. I mean, if you say, how much are you going to lose? Well, by week 10, you'll lose, 15 pounds or whatever. How much do I usually off by? About 1.3 pounds. Oh, that's pretty good. So it's within range. Obviously, the smaller S is, the better. By the way, the smaller S is, the larger R is. If R squared and R are 100% or 1, then S is 0. I'll say it again. If R squared and R are 1, then S is 0. So let's say all the points on this lined up in a perfect line. Perfect line. Let's say they did. Then obviously R squared is 100% because all the variability is accounted for by the line. But S would be 0 because the typical prediction is off by nothing. So as they get away, as R goes down, S goes up. That's how they work in their inverses of each other. Okay, I hope that helped. That was fun. That is chapter 3, day 5.